In this video, we're going to focus on drawing the hybridization with a double bond. So we'll do the example of ethene. We've seen it already. We've described it conceptually, but now let's go ahead and represent it using energy level diagrams. So first, we're going to draw ethene's Lewis structure. And so we have a double bond there. And then we have our single bonds over here and over here. And I knew to space them out that way because if you remember, when you have VSEPR theory and you have multiple central atoms, you can just focus on one central atom at a time. So this can be carbon number 1, carbon number 2, and there's 3 regions around it. So they're going to be essentially trigonal planar around. That's how they space themselves out to minimize repulsion. And so before we jump into making energy level diagrams, what I like to do is I like to figure out what my sigma bonds are, what my pi bonds are going to be, also what the hybridization is going to be. And that helps to make my drawing a little bit easier after. So let's start with how many sigma bonds there are. There's 1 sigma, 2 sigma, 3 sigma, because there's one double bond, 4 sigma, 5 sigma bonds. So there's 5 sigma bonds. They're the direct overlap sigma bonds. And so we know, for example, between the C and the H, we're going to have sigma bonds. And we also have a sigma bond between the C and the C as well. So 4 of them are from the CH, and then 1 of them is from the CC. And we can figure out what type of sigma bond they are with the hybridization check. So for carbon number 1, we can check its hybridization. There's 3 regions, so sp2. So sp2 hybridization. And with carbon number 2, it should be the same because it's the same layout, but just to check, we have sp2. So also sp2 hybridization. So our sigma bonds formed for the carbon-carbon bond is an sp2 overlap, and that's going to be a sigma. And then the sigma for the carbon-hydrogen is going to be an sp2, and then hydrogen is simply s, right? Because there's only one region there, so sp2s sigma overlap. And the other thing we want to check out as well is how many pi bonds we have. So we have a double bond, which means that it's made up of a sigma, and then we have 1 pi, and that's going to be the unhybridized orbitals that make it. So just a reminder that we're going to have in our diagram somewhere some hybridization, but also some unhybridized orbitals that are left behind, so to speak. So this is really going to help us when it comes to drawing our diagrams out. It's really the same basic steps that we've seen before. We need to draw energy level diagrams for each atom involved in our molecule. And then afterwards, we can do the hybridization, promotion, mixing process. Let's start with the easiest one. We'll start with hydrogen first. So there's 4 hydrogens there. So I'm just going to draw it once and do times 4. So let's go ahead and do that. We have an energy level diagram for hydrogen. That's the 1s here. And I'll just say times 4 because there's 4 of them. Next, I'm going to do my energy level diagram for carbon. I'm going to make it unhybridized first. And remember, there are 2 carbons, so actually I'm going to leave some room. I'm going to make 2 carbons just to show you what's happening. So we'll do 1 carbon over here. And the first carbon is going to be sp2 hybridized in the end. So let's put the energy here because we want to show its energy on those arrows. And carbon is like this. So we have 1s2. We have this is a 2s there. And that's filled up as well. And then we have our (2p)4. So that makes sense. We have, no, I think there's too many electrons. Carbon's number 6. So there we go. That makes sense. So we have 2p2. Now, remember that carbon wants to form 3 bonds, right? So carbon does want to form 3 sigma bonds. So that means it needs 3 electrons available for bonding. So 3 electrons available for bonding. And right now it only has 2. So what I'm going to do is I'm going to do an electron promotion. I'm going to send this one up here. So that's our electron promotion. I'll call it EP, electron promotion. And then I'm going to mix. But the thing is, I want you to notice that we do have a double bond there, and that's made from unhybridized P. So I'm not going to mix all of them. I'm going to leave one of the P's unhybridized. It won't be part of the mix in the end. So we'll do our mix over here. And the hybridized ones will be the S and 2 of the P's in between the S level and the P level we have originally, because they're at some intermediate level. And they're single like this. So 1, 2, 3. These are 1 part S, 2 part P. So they're all sp2, 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 specifically 2 sp2 because they're in the second energy level. But we left one of them. So really it's just this, this, and this that have mixed. And the other one just stayed where it was. It stayed above as an unhybridized one. So we can put it, let's say, over here. At the same energy level as where it was before. So this one here is unhybridized. So I'll just call this unhybridized. And I know I need that because I have a multiple bond there. I have a double bond. So it has to be an unhybridized orbital. And I'm going to draw the other carbon in the same way. So this is one carbon, carbon number 1, carbon number 2, doesn't really matter. And then we'll do the other carbon in the same way, because if we look at the atoms, we saw they're the same hybridization and they're set up the exact same way anyway. So it makes it nice and easy for us. So 2 electrons in the 1s, 2 electrons in the 2s, and then we have our 2 electrons in the 2p. We need 3 bonds for sigma bonds. We need 3 single electrons, so we'll promote 1. And then we'll mix. And we need to realize that when we mix or hybridize, we need to keep 1 behind, or where it was, for that indirect overlap. And then so only really the 2s and 2 of the 2p's are going to be coming together. So these are going to be involved in the sigma bond formation because they're hybridized. So sp2, 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 and then 1 is left behind at the energy level it was at before, the original energy level. And this is an unhybridized one as well. And so now what we're going to do is we're going to go and circle what corresponds to what in these diagrams. We'll do some color coding here. So let's start with our sigma bonds. So all the CH over here, they can be explained by essentially each one. I'm going to draw this out just so you could do times 4, but I just want to show you what's happening. I want to be very specific with you here. So I'm just going to draw each hydrogen. It's not necessary to do this all the time. Again, times 4 would have sufficed, but I want to really show you what's happening. So each of the sigma between C and H is basically, so this bonding with this. We'll call this carbon number 2 here. Okay, so that's this one. And then this with this, that would be that one there. Okay, and then this is carbon number 1. So this with this, that would be that one. Doesn't really matter which one, just know that it's one of them. And then this with this, that'd be that one. Okay, so we've shown the sigma bonding between the C and the H's. And let's choose a different color for the sigma bonding between the 2 C's. So here's the sigma bond between the 2 C. That'll be this and this. That's that there. Okay, and then we have a pi bond. So the pi bond, let's do purple. It's right here. That's going to be the indirect overlap between the unhybridized ones. I'll make it a dotted line to show indirect overlap. You don't have to do that, but it's nice to do that to remember it's indirect overlap. This is the pi bond that formed. So what we've just done here is we've shown the hybridization process and explained the sigma bonds involved in this molecule. We essentially said that we have the CH sigma bonds are direct overlap between 1s of H and 2sp2 of C. And then we saw that the CC pi bond is the direct overlap between 2sp2 of each carbon. And then we saw that the pi bond is the sideways or indirect overlap of the unhybridized p of, let's say 2p of each carbon. And again, the unhybridized stay at the same energy level because they're not part of the hybrid orbitals. They're not energies in between the s and the p. They're just at their original energy level since they stayed where they were. So we explained that. We showed that in the diagram, and I wrote it in words here if you want to explain it. Nice and simple. You don't have to write big paragraphs, just kind of 1 point for each thing you're trying to explain. And then we can do our drawing at the end here. So for the drawing, what I typically like to do is I'll start off with just sort of one aspect at a time. We'll start off with our pi, with our sigma. So I'll just draw my carbons here. And I'll basically say, okay, well, the sigma between this carbon and this carbon is an overlap between their sp2s here. So we'll do our up and down arrows here. And that would be the sigma bond over here. That's the sp2, sp2. So sp2, sp2. And then the other sp2s for each of the carbons can be drawn like that. Very similar to the Lewis structure you drew, actually. And we can do the hydrogens here. So first I do the sigmas. So up, down arrow, up, down arrow, up, down arrow, up, down arrow in the regions of overlap. And these are the S and sp2 sigma bonds. S and sp2 sigma bonds. Just like that. And so sigma here and sigma here. Sigma, let's make that look more like sigma. This is S, sp2, sp2. So now, in a different color, I'm going to show the unhybridized p orbitals. So notice the sp2 orbitals are not shaped like p orbitals anymore. They have a hybrid shape as opposed to a p orbital shape, a dumbbell. I'm going to do this in different colors. So the carbon has a remaining unhybridized p. We'll do it as a dumbbell. Didn't mean to do it like that. Let's redo that. There we go. And this carbon also has an unhybridized p. Like that. And they have their electron in there. Like that. And there's an overlap on top here and here as well. It looks like 2 pi bonds, but it's actually only 1 because it's made from 1 p on each carbon. So this is the pi bond that makes up, that's part of the double bond, which is made up of the 1 sigma and the 1 pi. So this is 1 pi bond here specifically. So what we've just done is an orbital representation diagram. Essentially, when we have questions like this, we start off with the Lewis structure. We try to label the Lewis structure as best we can with the sigma bonds, the hybridization involved, how the sigma bonds form, and also the pi bonds. And once you do that, it makes our lives easier because we know what we're supposed to be drawing. We don't have to look at our energy level diagrams to try to figure it out like a puzzle. We know what to draw if we understand how to get information from our Lewis structure. And then I essentially just drew all the atoms involved. The hydrogens were just 1s, as we know, and the carbons were the ones that were sp2 hybridized, so I had to make that happen by promoting electrons and mixing and leaving one of the p's behind for each as unhybridized for the pi bond. I knew to do that because there was a pi bond there specifically, and the only way I kind of knew that is because I did my Lewis structure at the beginning, and I was able to figure that out from the Lewis structure. And even if you didn't do your Lewis structure, if I gave you the structure, you'd probably have to figure that out anyways based on the amount of bonding, but it's still visualizing it in your head. So before we move on to the next video, which will go over a triple bond, you should be able to do this question here. So watch this video, retry it on your own until you get it with no mistakes and every aspect of it makes sense. Make sure you can do label diagrams and explain things in nice point form to see where all the different parts are coming from, and make sure you can connect all the label diagrams to each other. The Lewis diagram, VSEPR diagrams, the orbital energy level diagrams, the orbital representation with the balloon animals. If you can do all that, then you can move on to the next video to watch triple bond formation.